In this video lecture, I will discuss the properties of the capacitor as a passive component in electronic circuits. If we take two parallel metal plates, separated some distance apart by an insulator, such as air or ceramic, for instance, we have created a capacitor. The insulating material is also called a dielectric. Let us consider now a circuit consisting of a battery Vi, a capacitor, and a switch. A switch is a device that can work in two possible conditions. Either it is open, and in that case it behaves like an open circuit, or it is closed, and in that case it behaves like a short circuit. Let's start with the switch in the open condition. In this case, no charge can move in the circuit as the circuit is open. If we now close the switch, the capacitor will be connected in parallel with the voltage source. An interesting thing occurs in this case. Electrons are pumped out the negative battery terminal and collect on the lower plate of the capacitor, while electrons are drawn away from the upper plate into the positive battery terminal. The top plate becomes deficient in electrons, while the lower plate becomes abundant in electrons. Very quickly, the top plate reaches a positive charge plus Q, while the bottom plate reaches a negative charge minus Q. Since the capacitor is in parallel with the voltage source Vi, based on Kirchhoff's law, we can say that the same voltage can be found across the capacitor. Moreover, since we have a charge plus Q on the top plate and the charge minus Q on the bottom plate, we will have a field between the two plates going from the positive charge towards the negative charge, and the magnitude of this field, let's call it E, will be given by Vi divided by D, where D is the distance between the two plates. Now, if we open the switch again, the charge, the electric field, and the voltage remain on and across the capacitor. The reason for that should be quite intuitive. In order to make the negative charge on the bottom plate disappear, we would need to take electrons away from the bottom plate. On the other hand, in order to make the positive charge on the top plate disappear, we would need to bring electrons on the top plate. So what we would need to do is we would need to move charge across the circuit. But now that the switch is open, the circuit is open, so no charge can move in the circuit. So the charge stays where it is on the plates of the capacitor, and the field and the voltage across the capacitor do not change. In the case of a real capacitor, leakage currents or parasitic currents due, for example, to bad insulating material may discharge the capacitor. So, if we wait long enough, a real capacitor will discharge. If we want to quickly discharge a capacitor, we can connect the two plates using a wire. So we can short circuit the two plates. In a circuit, the capacitor can be found to be represented by a symbol like this or by this other symbol. The characteristic parameter of the capacitor is called the capacitance, typically indicated with the letter C on the side of the symbol. In a capacitor, the capacitance is the ratio between the charge Q on the plates of the capacitor and the voltage across the capacitor. So C is equal to Q over V. The unit of measurement of the capacitance is the farad, indicated with the letter F. By definition, 1 farad is equal to 1 coulomb divided by 1 volt. Based on the definition of capacitance, if we apply a voltage E to a capacitor with capacitance C, then the charge on the two plates of the capacitor will be given by the capacitance C times the voltage E applied to the capacitor. On the other hand, if we have a capacitor with capacitance C and charge plus Q and minus Q on the two plates of the capacitor itself, then the voltage Vc across the capacitor will be given by Q divided by C. The capacitance in a capacitor can be calculated once the geometrical feature of the capacitor itself and the nature of the dielectric material between the two plates are known. So suppose we have a capacitor consisting of two parallel plates with area A. Suppose the distance between the two plates is D. Let's assume that the dielectric material used as an insulating layer between the two plates has permittivity epsilon. The permittivity epsilon is given by epsilon 0, which is the vacuum permittivity, times epsilon d, which is called the dielectric constant or relative permittivity. The vacuum permittivity epsilon 0 is approximately equal to 8.85 times 10 to the minus 12 coulomb square over Newton per meter square, or farad per meter. The relative permittivity epsilon d is characteristic of the dielectric material used as an insulating layer between the two plates of the capacitor. Now assume we have a voltage drop V between the two plates of the capacitor. As a consequence, we will have a field E between the two plates given by V divided by the distance D between the two plates. In order for the voltage V and the field E to be there, we will need a charge plus Q and a charge minus Q on the top and the bottom plate respectively of the capacitor. Suppose we now enclose the top plate of the capacitor into a hypothetical closed surface. There is a law, due to Gauss, saying that the net flux of the electric field through that surface is equal to the charge inside the closed surface divided by the permittivity epsilon. In our case, the flux of the electric field can be demonstrated to be given by the area A of the plates times the field magnitude E. From the last equation, we get that the charge Q can be written as the permittivity epsilon times the area A times the magnitude of the field E. Now we know that by definition, the capacitance C is given by the charge Q divided by the voltage across the capacitor V. By replacing Q in this expression, we get epsilon, the area A, times the field magnitude divided by V. But we know that the field is the voltage divided by the distance between the two plates. So we can write again this expression as epsilon times A times the voltage V divided by D times again the voltage V. We can simplify V and V at the numerator and at the denominator, and we eventually get epsilon A divided by D. This final result tells us that the capacitance can be computed as the permittivity epsilon of the dielectric material times the area of the plates divided by the distance between the plates. So the capacitance is directly proportional to the area and inversely proportional to the distance between the plates. Suppose now we connect a capacitor to a source generating a voltage which changes with time. Just to clarify things, here we are assuming that the voltage Vi applied to the capacitor is changing linearly with time, but this is not strictly necessary. Now we know that the charge Q on the plates of the capacitor is proportional to the voltage Vc across the capacitor through the capacitance C. Now for any increase delta Vi in the voltage applied to the capacitor, we get an increase delta Vc in the voltage across the capacitor exactly equal to the increase in Vi. On the other hand, for any increase delta Vc in the voltage across the capacitor, we expect to get an increase in the charge on the plates of the capacitor given by the capacitance C times the increase in the voltage delta Vc. Let's assume that delta Vc is the change in the voltage across the capacitor taking place in a time delta t. In the same time, the charge on the plates of the capacitor changes by delta Q. We can eventually say that the rate of change of delta Q, so delta Q over delta T, is equal to the capacitance C times the rate of change in Vc. If we take the limit for delta T going to 0, the change in charge Q and voltage Vc will become infinitesimal. So for delta T becoming smaller and smaller, we get eventually that the time derivative of the charge is equal to C times the time derivative of Vc. By definition, the time derivative of the charge is a current, and in particular, this is the current IC flowing through the capacitor. While discussing the operation of the capacitor, I've been talking about a current flowing through the component. But is a current actually flowing through the capacitor? The two plates of the capacitor are actually separated by an insulating layer, which should prevent any current from flowing from one plate to the other. Let's see what happens instead. If we increase the voltage across the capacitor by an amount delta Vc, we will have an increase by delta Q of the charge on the top plate of the capacitor and a decrease by the same amount of the charge on the bottom plate. This change in the amount of charge on the two plates is due to the fact that as a consequence of the change in Vc, we will have a certain number of electrons leaving the top plate and the same amount of electrons moving towards the bottom plate. Moving charge is actually a current. So we will have a current IC going towards the top plate and an equal current IC at the bottom plate going outwards. Remember that by convention, the current is made of moving positive charge carriers. These currents are not going through the insulating layer. A current IC is moving towards the top plate. A current IC is moving from the bottom plate. Now let's close the capacitor into a box. What we see now is a current IC flowing into the box from the upper terminal and the same current flowing out of the box from the lower terminal. Everything goes as if a current IC were flowing through whatever is inside the box. For this reason, we will be talking about the current IC as flowing through the capacitor, although this is not exactly what happens in the component. So there exists a differential relationship between the current flowing through a capacitor, IC, and the voltage across the same capacitor, Vc. The relationship is IC is equal to the capacitance C times the time derivative of Vc. From this relationship, we can get an integral one. In particular, starting from the above equation, we can write that C dVc is equal to IC in the t. We can then take the integral of both members of the equation, and in particular we can write that C times the integral between Vc at some time t0 and Vc in t of dVc is equal to the integral between t0 and t of IC in the tau. The first member of the equation yields C times Vc in t minus Vc in t0, which is equal to the second member of the equation, so the integral between t0 and t of IC in the tau. From the last equation, we can write Vc as a function of the time equal to Vc at time t0 plus 1 over c, the integral between t0 and t of IC in the tau. Vc in t0 is called the initial value of the voltage across the capacitor. Note that in choosing the polarity of the voltage drop across the capacitor, Vc, and the direction of the current flowing through the capacitor, we have complied with the passive sign convention. A capacitor can also be seen as an energy storing device. The amount of energy accumulated by a capacitor depends on the amount of charge on its plates or on the voltage across them, which is more or less the same given the fact that the charge is proportional to the voltage through the capacitance C. To get an insight on how a capacitor can be made to work as an accumulator, consider this circuit where we have a battery VB, a capacitor, and a resistive load. Let us first connect the capacitor to the battery. The capacitor will charge to a voltage VB. A charge Q will be located on the top plate, a charge minus Q on the bottom plate, with Q equal to C, the capacitance of the capacitor, times the voltage VB. Now let's disconnect the capacitor from the battery. The situation, as far as the voltage across the capacitor and the charge on the plates, will not change. Now let's connect the capacitor to the load. Due to Ohm's law, as soon as we connect the capacitor to the resistor, a current IR equal to VB divided by R will flow through the resistor. The same current will flow through the capacitor. As the current flows, the charge on the two plates of the capacitor will decrease, as well as the voltage across the capacitor, which will be now smaller than VB. Remember that a current is just charge in motion, so the current IR will take charge away from the capacitor. And this is the reason why the charge on the plates and the voltage across the capacitor reduce. As a consequence of this reduction in the voltage across the capacitor and across the resistor, which is in parallel with the capacitor, the current IR will also in turn decrease. The charge on the plates will continue decreasing, although at a smaller rate. The current will stop flowing when no more charge is left on the plates and the voltage across the capacitor becomes zero. Of course, the larger the capacitance, the larger the amount of charge accumulated on the plates when the capacitor is connected to the voltage source, the longer the time needed to take it away from the capacitor and the time during which the capacitor can actually provide current to the load. We will discuss more accurately the time evolution of the current and voltage in a capacitor connected to a resistor in a subsequent video lecture. We may now wonder how the energy accumulated in a capacitor depends on the capacitance and on the voltage across the capacitor or the charge on the plates of the same capacitor. In order to find this out, let's consider the following circuit consisting of a current source and a capacitor. Let's assume that the current I generated by the current source is non-zero between time t equal to 0 and time t equal to delta t, like in this time diagram. The current source will bring charge onto the plates of the capacitor, therefore increasing the voltage across the component. The instantaneous power Pc delivered by the current source to the capacitor will be given by Vc times Ic by definition of power, where Ic, of course, is equal to the current I. Now we know that by definition the energy, and in this case the energy accumulated in the capacitor, let's call it Ec, is equal to the integral between 0 and delta t of the power Pc in dt, which is equal, by replacing Pc with its expression, to the integral between 0 and delta t of Vc times Ic in dt. Now we know that in a capacitor, the current Ic is equal to the capacitance times the time derivative of the voltage across the capacitor. Therefore, we can rewrite the energy as the integral between 0 and delta t of Vc times c times the time derivative of Vc in dt. Let's assume that the capacitor was fully discharged at the beginning, so at t equal to 0. Therefore, Vc in 0 equal to 0. Then, with a change of variable, we can rewrite the integral as the integral between Vc in 0, which is 0, and Vc in delta t, of Vc times c in dVc. Eventually, this integral yields 1/2 cVc0 squared, where Vc0 is simply Vc computed in delta t. We know that the voltage in a capacitor can be written as the charge divided by the capacitance, so in particular Vc0 can be written as the charge in delta t divided by the capacitance, which we rewrite as Qc0 divided by C. Therefore, the energy accumulated in the capacitor can also be written as 1/2 Qc0 squared divided by C. Let us consider now the circuit consisting of a battery generating a voltage VB connected to two capacitors in series, C1 and C2. The battery will move electrons to the bottom plate of C2, where a charge minus Q will collect. The same current bringing electrons to the bottom plate of C2 will take electrons from the top plate of C1, where a charge plus Q will collect. A charge minus Q will then be induced at the bottom plate of C1, and the charge plus Q will result at the top plate of C2. The voltage across C1, let's call it VC1, will be given by Q over C1, while the voltage across C2, let's call it VC2, will be given by Q over C2. Now we can write Kirchhoff's law for the loop as VB equal to VC1 plus VC2, where we can replace VC1 and VC2 with their expression as a function of Q and get Q over C1 plus Q over C2, or Q times 1 over C1 plus 1 over C2. We can eventually write VB as Q over CS, where CS is equal to 1 over C1 plus 1 over C2, or C1, C2 divided by C1 plus C2. Therefore, from the standpoint of the battery and of the charge the battery has to move, the two capacitors C1 and C2 in series behave like a single capacitor with the capacitance CS equal to C1, C2 divided by C1 plus C2. In the case of n capacitors, in series, then the equivalent capacitance CS is given by 1 over the sum for j going from 1 to n of 1 over Cj, where Cj is the capacitance of the jth capacitor. This circuit we have just been discussing is also called a capacitive divider. In a capacitive divider, the input signal is applied across the series of the two capacitors, while the voltage drop across one of the two is taken as the output signal. Let's take, for instance, the voltage across C2 as the output signal. We know from the previous discussion about the series of two capacitors that the charge Q collecting on the plates of the capacitors is given by VB times CS, or VB times C1, C2 divided by C1 plus C2. On the other hand, we can also say that the same charge Q is equal to VO times C2. From the two equations, we can say that VOC2 is equal to VB C1 C2 divided by C1 plus C2, from which we eventually get that the output voltage is equal to the input voltage VB times C1 divided by C1 plus C2. Note that, as in the case of the resistive divider, also for the capacitive divider, the output voltage is always smaller than the input voltage, given the fact that the multiplicative factor C1 over C1 plus C2 is always smaller than 1. Consider now the following circuit consisting of a battery generating a voltage VB connected to two capacitors C1 and C2 in a parallel configuration. Since the two capacitors are in parallel with the battery, the voltage across them will be the same and equal to VB. If the two capacitors have different capacitance, the charge on the plates of the two capacitors will also be different. So we will have a charge Q1 in the first capacitor and the charge Q2 in the second capacitor. By definition, Q1 is equal to VB times C1, while Q2 is equal to VB times C2. Note now that the two capacitors have the top plate connected together with an ideal conductor. So these two plates actually behave like a single plate carrying a charge which is just the sum of the charge Q1 and Q2. Also, the bottom plates of the two capacitors are connected together with an ideal conductor, so they behave like a single plate with a charge overall given by minus Q1 minus Q2. Now, Q1 plus Q2 is equal to VB C1 plus VB C2, or VB C1 plus C2, which we can rewrite as VB times CP, where CP is equal to C1 plus C2. So from the standpoint of the battery and of the charge it has to provide to the capacitors, the two capacitors C1 and C2 in parallel behave like a single capacitor with a capacitance equal to the sum of C1 and C2. In the case of n capacitors in parallel, the equivalent capacitance Cp will be given by the sum for j going from 1 to n of Cj, where Cj is the capacitance of the jth capacitor.